Welcome to lesson 31. This is the last of your official lessons in Math 135 telecourse. Now there are some addenda which maybe you've gone to earlier or maybe you want to go to now. So anyhow, this is the last official lesson. It is on binomial expansions. So let's get started. Now, if I locked you in your room and said you're not allowed to leave until you multiply 2x minus 3y out to the 9th power, I have confidence that you would eventually get it. Now, I'm also running like crazy when I let you out of the room. But there's got to be an easier way, and that's what we're really exploring today. However, besides just expanding these binomials up, which we may want to do for some algebraic work, this also, the binomial expansions we're going to be looking at are very useful in probability. And if we had time, we'd explore some problems like, what's the probability that a family of 5 has 3 girls and 2 boys? It can be a very fun kind of probability problem to work on. And it uses the binomial theorem that we're looking at in this particular lesson. Okay, now to get you to that point, I want to start out with something really easy. Okay, so play along with me. What is a plus b? The most basic binomial I can give you, raised to the 0th power. Well, we all know that's 1. Now, granted, you might wonder, why did she write it like that? Play along. Now, if I take a plus b and I raise it to the 1st power, you know that means it's going to be just a plus b. But again, I wrote it kind of in an odd format. It is correct. Play along. Now, if I take a plus b to the 2nd power, I bet some of you guys are totally cool with doing that in your head. A squared plus, remember you have outers and inners, 2ab plus b squared. Yeah. Okay. Now, the next one I don't think is going to be obvious. So the question is, how do I get a plus b raised to the 3rd power? Well, you know, it's the same thing as asking you what is 7 cubed, in a sense. If I ask you, and you don't have a calculator, what is 7 cubed, you must tell me. You're going to take 7 times 7 and get 49, right? Then you're going to take that answer times 7. So do the exact same thing with your polynomials. Hey, have you ever made the connection that much of what we do in algebra is simply arithmetic, only with letters? There's a lot of parallels between what we do with our numbers and what we do with our letters. All right? Well, that means that I need to take a plus b times whatever I get when I square a plus b. Well, I've already done that multiplication. So I have a plus b times a squared plus 2ab plus b squared. And hopefully you know how to do this multiplication. I'm going to first distribute the a all the way through, and that gives me a cubed plus 2a squared b plus ab squared. Then I'm going to take the b and distribute him through. So I get an a squared b. I'm going to write him right underneath there so that I can line up my like terms. You know, that's what we do over here too. And then b times this gives me 2ab squared, and b times b squared gives me a b cubed. Because then when I combine all my like terms, I get an a cubed, 3 a squared b plus 3ab squared plus b cubed, which, it was not nice. Which is what it tells me right here. 1a cubed plus 3a squared b plus 3ab squared plus 1b cubed. And one more to do. We want to take that answer times a plus b, because we want to go to the 4th power. So I'm going to take that answer and multiply it one more time. Okay. Multiplying the a through each of those 4 terms, I get a to the 4th plus 3a cubed b plus 3a squared b squared plus ab cubed. Now take the positive b and distribute him through, and we get another a cubed b, 3a squared b squared, 3ab cubed, and we get a b to the 4th. And adding up the like terms, you'll see we get a coefficient of 1, of 4, of 6, of 4, and of a 1. All right, and I have that all nicely written here. And some of you might know exactly why I'm writing it out in this triangular kind of form. Now, I do want you to notice what's kind of interesting here about the exponents. For example, and it might be easiest to look at our 4th power here, we go 4, 3, 2, 1, 0 as the exponents on the a. And if you look at the b's, which was the 2nd term, he starts at the 0 power, 1, 2, 3, and 4. Well, that's kind of interesting. And you'll notice the same thing happens on all the previous ones as well. One other thing you want to notice about your exponents is that for each term, the sum of my exponents is 4. It's 4, 4, 4, 4, which was the power to which I was raising it. Okay. Those kinds of things are very helpful to see. And by the way, some of you might be biting at the chomp on this whole idea of the coefficients. Now, I do want to mention this coefficient. I'll hopefully have it all come together in a few minutes. But notice that we have 1, 1, 1. We have 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. It's a nice little pattern developing here. And I want you to understand from where did they come? They're called your binomial coefficients, and they just came from the multiplication and then the addition of like terms. It's just what happened from multiplying this very simple binomial up. All right? We had no numerical values from the beginning other than 1. So these just naturally occurred through the multiplication property or the multiplication process. So what is the pattern? Well, I'm going to give you the big binomial theorem. Now, I wish I had a drum roll set up because this is a huge puppy coming in here. Now, you need to write that all over your notebook and let everybody know just how smart you are in math. This is a pretty scary looking thing, but you know a lot of what's here already. We have a binomial, a plus b, and we're raising it to the nth power. So that n, by the way, means to what power I'm raising this. Like on the very beginning, I had us raising it to the 9th power. Okay. Then on this side, the first thing you run into is sigma. Well, we've been working with sigma in our sequences and series, technically our series. So you know that's a sum. And you know the idea that you're starting k at 0, and then k is going to be 1, then k is going to be 2, all the way up until you hit n. Now we're going to bypass this for a moment because you might think that I've mistyped it, but I really haven't. And then you'll notice that we have the a and the b from the beginning binomial sitting here, and I'm explaining here how to get the exponents. Okay, so now what we need to explore is what in the world is this? This is probably the only part that you're not already familiar with, although you might be. Hey, and by the way, you might notice that it's being multiplied on to the a and the b. That is, by the way, your binomial coefficient. And if you've got your notes handy on this, you might want to just write that in right now. That is what is called your binomial coefficient. And I might be getting ahead of myself, but that's where that whole 1, 3, 3, 1, 1, 4, 6, 4, 1. Those numbers that I said had such a nice pattern, yeah, that's what's giving me those numbers. Now let's explore that particular notation just a little bit further. What in the world is this? Well, you might have seen it previously written with a capital C, and the N and the K are subscripts, the N before and the K afterwards. This is technically what's called a combination. A combination. If you did any work in the past in probability, a combination is how many ways something can happen when order does not matter. Like if I have 8C3. Let me give you an example of what this means, and we might be able to connect to some previous knowledge you have. If I have 8 people in the room, and I want a committee of 3 people, and those 3 people are going to get assigned to a task. It makes no difference in what order the 3 are selected. It's just that whichever 3 of the 8 I pick, they form the committee. This is saying out of the 8, I'm going to choose 3 people. Now, as it turns out, in order to solve that particular problem, we have a formula. Now, let me show you. There's a second notation. We sometimes use that capital C, which is probably what you have seen in the past. Or we write it, it looks like it's a fraction, but there's no fraction bar. Don't put the fraction bar. And then we see that it ends up being 8 factorial over 3 factorial, and then 8 minus 3 would be 5 factorial. Okay, and I think we've run into that factorial in a previous lesson as to what that means. It's 8 times 7 times 6 times 5. So we'd have 8 times 7 times 6 times 5, 4, 3, 2, 1, 3, 2, 1, 5, 4, 3, 2, and 1. Now, I know I don't have to write the ones, but they just kind of make all the patterns work out nicely. And I can do a lot of canceling here, and I end up with 56. And if you'd like to explore that, you could write down the names of 8 people and figure out how many committees you could make with 3 people, and you'd find that there are 56 of those. I know, that seems like a little more than you might want to try. But anyhow, you might also want to look on your calculator. Now, generally in your calculators, it's going to be an NCR. I just use the K because that's a nicer one in the binomial theorem, in my opinion. But a lot of your calculators are going to have an NCR button. Sometimes it is in the probability menu. So you may need to find the probability menu, then find your NCR button, and you are going to be responsible for figuring out how your calculator handles the input in order to get that answer. So for example, you know that 8 choose 3 should have an answer of 56. You jot that down and you keep playing with your calculator until you get it giving you these answers correctly. The correct answer there is 56. In some cases, you would put in the 8, then select the NCR, then put the 3, and hit equals. Other calculators handle it in different ways. Learn yours. Okay? So I said find each of the following using the given formula here, which we generally give you this formula on the final exam if you need to use the formula. If I were you, I would strongly urge you to find out how to use the button on the calculator. Now let's first find 5 choose 2. Okay, now for 5 choose 2, I'm writing it this way because this is the way you're going to see it in your binomial theorem. But the way that you think about it for your calculator would be 5C2. Okay? Now that's going to be 5 factorial over 2 factorial times 3 factorial, and that should be 10. Okay, you can run the numbers. I'm giving you these values so that you can do some practicing. Make sure you get the right values. Now for 10C3, which means the same thing as this notation does. I want you to get comfy with the notation. That's going to be 10 factorial over 3 factorial times 7 factorial. And let's see here, that's going to leave a 3, 4. I think that's 120. Should be 120. Okay. And then the last one there, I'm just kind of playing with trying to up your algebra comfort level here a little bit. How about this 2n plus 2, 2 at a time? Your calculator's not going to give you that answer unless you're working with one that has a CAS system on it, which you can't use on your final. Okay? So let's see if we can do that just working it out on our own. We know that it's going to be 2n plus 2 factorial, because it's always this top number, factorial, over the bottom number factorial. I think I want this space. Times, then for the second one, we subtract these. What do you get if you take 2n plus 2 and you subtract 2? Don't you just get 2n? Okay. Now we're going to simplify this because I want you to do the algebra here with me. That's going to be, well, when I start a factorial, I started at that number. And then times 1 less than this number. What would be 1 less? Be 2n plus 1. And what's 1 less than that? 2n. And what's 1 less than that? 2n minus 1, and 2n minus 2, and 2n minus 3. And that keeps going on forever. Well, not forever. But I don't know when I get to stop it. Now, for this, I have 2 times 1 for the 2 factorial. Now, for this guy, I start him at 2n. And then what's 1 less than 2n? 2n minus 1, and 2n minus 2, and 2n minus 3, and I just keep going. And you find if you do use this formula that there's lots of canceling that happens. So you always go looking for what you're going to be able to cancel out. And I could factor a 2 out of here. That's 2 times n plus 1, and I can cancel the 2's. So I end up with n plus 1 times 2n plus 1. That's what this nasty combination will actually equal. Huh, that was scary, wasn't it? Okay. Now, by the way, some of you, I said, might be biting at the chomp there at the beginning because you might have heard of Pascal's triangle. You might do some research on the mathematician here. His first name is Blaise, kind of a cool first name. And he's a very interesting man. I've read one historian describe him as the greatest might have been in mathematics. But what's interesting about this is that it's a very quick and easy little pattern to discover because you always have ones on the outside and then you add. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 1 is 3. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And a 1 on the outside. Hey, do you remember these numbers? 1, 4, 6, 4, 1? Those were those binomial coefficients back in the very beginning. Yes. This is a quick way to sometimes get your binomial coefficients. What I'm doing is I'm giving you two options. you can use your calculator and you can run these combinations in order to get your binomial coefficients. And at times, that's my preferred method. But for small exponents, I kind of like running Pascal's triangle because it's very quick and easy for me. If I'm sitting at this row, I just say 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 5, and 1. Very quick and easy to get the first 6, 7 rows. All right? Hey, and one of the other things that I'd like to do is, first off, let me show you that these are actually numbered, but this very top row is called the 0th row. So essentially, if we say go to the 4th row, it's the number that has the 4 in the second spot, okay? Keeping in mind that that is the 0th row. But I also want to show you that essentially this triangle of Blaise Pascal is 0 things, 0 at a time. This is actually our combinations. The first row is 1 thing, 0 at a time. Let me try that in black. Might show up better. 1 thing, 0 at a time. 1 thing, 1 at a time. The second row is 2 things, 0 at a time. 2 things, 1 at a time. 2 things, 2 at a time. The third row is 3 things, 0 at a time. 3 things, 1 at a time. 3 things, 2 at a time. 3 things, 3 at a time. Now, to get a good feel for this, why don't you grab your calculator and check to see, let's say, 9 choose 4. 9 choose 4. Did you get it? Okay. Now, I can go to the 9th row. This is 9, 0, 9, 1, 9, 2, 9, 3. You should be looking at a 126 on your calculator. Are you? Hopefully. So play around with this, and what I'm saying is, sometimes this is a good option for finding those binomial coefficients. Sometimes I want to run the combinations on my calculator. It all depends upon how big it is. Like, I'm not going to write this triangle out to the 15th row. That's just too annoying. It would be then more time efficient to run my combinations. Hey, you might also notice that there's a lot of symmetry. Oh, there's wonderful patterns. You could Google Pascal's triangle and play for hours and hours and hours at the number patterns that are in this. But you'll notice that there's symmetry as you move in. 1, 5, 10. 1, 6, 15, 20. The reason I'm telling you that is that as you find those coefficients on your calculator coming from the left side, you're also finding them coming from the right side. Just a thought. Okay, so let's practice now doing some expanding. I've got x plus y and I want to raise it to the 4th power. Now we did this at the beginning by actually multiplying that all out. Okay? Now let me take just a second and actually write this with the whole big binomial theorem idea. We have x plus y raised to the 4th, and that's going to be the summation as k goes from 0 up to 4 of 4 things k at a time, first term x raised to the 4 minus k times y raised to the k. Okay? What I want to do is show you how this formula can be helpful in expanding these. Remember, you know what this summation means. I'm going to start with k being 0. So I would have 4 things 0 at a time, x to the 4th, y to the 0. Okay, k is 0. Now, plus, this time, k is 1. So I have 4 things, one at a time, x to the third, y to the 1. Plus 4 things 2 at a time, x squared, y squared. 4 things 3 at a time, x to the first, y to the third. Plus 4 things 4 at a time, x to the 0, y to the 4th. Now take a second and make sure you know where all of these numbers are coming from, because it's really not that hard once you get over the scariness of the formula. Now I need to go and find what is 4 choose 0, 4 choose 1, 4 choose 2. I can grab my calculator, or I can come over here and say, oh, well, it's these numbers sitting in the 4th row. Why the 4th row? Because I'm going to the 4th power. Whoops. Okay, so I have got 1 plus 4 plus 6 plus 4 plus 1. Those are my binomial coefficients. They came about simply from the multiplication process. Now this is going to be x to the 4th, y to the 0 is just 1. X cubed y, x squared, xy cubed, and x to the 0 is 1. I get a y to the 4th. And you do not have to write those ones if you don't want to, but there you go. All right? Now, by the way, here's the really quick way. Once you get comfortable, and I wanted you to see how that formula would be written out. Here's what I do when I see that 4. I go immediately to Pascal's triangle because it's only the 4th power. And I say, all right, x plus y raised to the 4th. That's going to be 1 plus 4 plus 6 plus 4 plus 1. Then I go in and I know this first term is going to start at the 4th power. And he's going to decrease in power by 1 each time. And he's to the 0th power there. I guess I can write it. The second term in the binomial starts at the 0th power and increases by 1 each time. And in case I get crazy because I'm talking while I'm writing, I always double check that the exponents add to the power. And they do. And you could clean that up if you want, but you get exactly the same thing. And you see how quickly that was done. Okay? Well, let's try number 2. And we're going to do this the quick way. All right? We're going to take w plus 3 and raise that to the 7th power. Okay. Now, since I have Pascal's triangle, I'm going to come over here and grab these coefficients. Now, if I didn't have Pascal's triangle, I could grab my calculator. This is 7 choose 0, 7 choose 1, 7 choose 2, and so on down the line. But I say it's going to be 1 plus 7 plus 21 plus 35 plus 35 plus 21 plus 7 plus 1. Hey, and something interesting is that you see one more term here than your power. And you might kind of double check that. That'll always happen. And that's because you're starting with k being 0. All right? Now, I start my first term at what power? At the power I'm raising this binomial up to. So it's w to the 7th, to the 6th, 5th, 4th, 3rd, 2nd, 1st, and 0. The second term starts at the 0th power and increases by 1 each time. Okay? Now I've got a huge warning for you right now. I often see students in this situation with plus signs just randomly all over the place. Remember I said just a moment ago, you have one more term than your power. And terms are separated by plus and minus signs. For each of these terms in your binomial expansion, the operation is all multiplication. This is all multiplication. So you end up with these 8 distinct terms, okay? Don't just randomly throw plus signs everywhere, please. Now, I'm not going to get this all multiplied out, but I'm going to multiply out some of it. This first term would simplify to w to the 7th. Now notice that we've got a 7 times a w to the 6th times a 3. I can make that 21 w to the 6th. That would be a nicer way of writing that, right? And here I have 21 times a w to the 5th times a 3 squared. Well, a 3 squared is 9, so I have 189 w to the 5th. Okay. Now this next one, I should be able to just multiply that all out, but so sorry, I'm not going to. So I'm going to have 35 times 27 w to the 4th. I apologize that I didn't think to run that ahead of time for you. And then I'm going to have plus 35 times 81. Where am I getting 81? Well, that's that 3 to the 4th times w to the 3rd. Okay. And here I have 3 to the 5th, which I happen to know. It's 243 w squared. Just go ahead and multiply these together for your final coefficient. This guy would be 3 to the 6th, which I think is 729. So I have 7 times 729 w. And then the last one, I think, is a 2187. Okay? I apologize that I don't have these multiplications, but these few right here, you just multiply those two together, and those become your new coefficients. Now remember, I use the term binomial coefficient. My binomial coefficient are these numbers coming out of Pascal's triangle. There are also those combinations in my binomial theorem. They're coming about just because of the process of multiplication. Now that doesn't mean they're my final coefficients, because you can see in this case the fact that I had a 3 as one of those terms changes my coefficients. Like my final coefficient here is a 21, not a 7. Why? Because the effect of the 3. Okay? All right. Going on, we have 3x minus 2y raised to the 5th power. And again, I may not be able to run all of my numbers on that, but that's okay. We get 3x minus 2y raised to the 5th. Now this one has 2 new twists for me. It has a number in each term, which, by the way, means this thing can mushroom to huge coefficients. But the other new thing is, ooh, we have a minus. Well, think back to pre-algebra days. You know, because your pre-algebra teacher taught you that to be safe with a subtraction, whenever you're in an unusual situation, change it to plus a negative. So that's what we're going to do here. We're going to change that to plus a negative so that this term is actually negative 2y. Okay. Now, I would go to the 5th row of Pascal's triangle. Now remember, I'm just doing that because that's easier right now since I have it all worked out than running those combinations on my calculator. But it's 1, 5, 10, 10, 5, 1. So I say 1 plus 5 plus 10 plus 10 plus 5 plus 1. Notice I only have 6 terms. Everything here is multiplied. Everything here will be multiplied all the way down through there. Okay? Now, I start my first term at the power to which I'm raising my binomial. And then I decrease it by 1 each time. Okay. Then I take my second term and I start him at the 0 power and I increase him by 1 in exponent each time. And remember, double check all along, these add to be 5. Yeah, I've not gotten off in my patterning here. Whoops, I have gotten off in putting my negatives. And then I'd have negative 2y raised to the 4th and a negative 2y raised to the 5th. Now take a moment there and make sure that you are with me on how I'm writing this all out, just using the patterns we discovered in the beginning. Okay? Now let's go in and simplify this. The negative 2y to the 0 power is going to be 1. Well, 3 to the 5th is 243. So I have 243x to the 5th, which is interesting because remember, ordinarily that binomial coefficient is 1. So how did I get the 243? It was because of that 3. Okay. Now, in this case, I'm going to have 5 times, well, 3 to the 4th is 81 x to the 4th, and I have a negative 2y to the 1st, which is just a negative 2y. I'm going to have to come by and do some more simplifying, huh? Okay. And then I've got 10. This is going to be 27x cubed. Now, in this case, I'm going to have a positive 4y squared. Plus 10, 9x squared. Now this guy's going to be what? Negative 8, right? Because it's a negative 2 cubed. I've got negative 8y cubed. And then I've got 5 times 3x times, this will be a 16y to the 4th. Whew. And then I have a 1 times a 1, and that would be negative 32y to the 5th. Last cleanup. We have 243x to the 5th. Multiplying, remember this is all multiply. 5 times 2 is a negative 10, so I have minus 810x to the 4th y. Well, I believe 4 times 27 is 108, so I have plus 1080 x cubed y squared. Okay, multiplying here. Remember, all of this has to get multiplied together. So multiplying the numbers, I'm using the commutative and associative properties of rearranging this, and I get negative 72 times 10. I get negative 720 x squared y cubed. Okay, rearranging, I get 80 times 3. I get 240 x y to the 4th and minus 32y to the 5th. Whew. That was quite a deal. Now, granted, that wasn't necessarily a bunch of fun, but that was a quicker process than writing out 5 of these and multiplying them one at a time to get to my answer. Okay? And by the way, I also have found, because over the years I've had students try all kinds of things, that often when they decide, I am just not going to learn that, I'm going to just multiply out 5 of those, you're going to make mistakes along the way. Now, this is rife with possibility for mistakes, but you have many more calculations if you're going to try to take that out to the 5th power on your own. Okay? Hey, by the way, one of the things I want you to notice is what happens to the signs in this case? The fact that this was a subtraction to start with instead of an addition, what did that end up accomplishing for us? Well, you might notice that what it does is it alternates the signs. Why does it alternate the signs? Well, because the negative is attached to the second term, and so any time that second term is raised to an odd exponent, you get a negative out of it. Oh, so what I have a tendency to do is, if I know I have a subtraction here, I just alternate the signs. Okay? You learn more and more shortcuts as you work through this. Oh, man. I got another guy to do. Square root of a plus 2 times the square root of b raised to the 8th. Oh, okay. Well, I noticed that it's a plus. That's good. All my signs will be addition. Okay. Okay. Now let's go back and grab that 8th row. Now this is where if I did not already have this computed, then what I might do is actually sit down and find those combinations. But I already have it, 1, 8, 28, 56, 70. Okay, so I say, all right, 1 plus 8 plus 28 plus 56 plus 70 plus 56 plus 28 plus 8 plus 1. Now, what have I been calling those numbers that I've put in there so far? Those are the binomial coefficients, okay? And now I take this guy and raise him up to the highest power, and then decrease them by 1 each time. I know that's really annoying to write all that, and you might decide, oh, I'm just going to do it without writing it. I think that's asking for trouble, because you can't get much lazier in writing than I am, but anytime I'm in a little bit of a tough situation, I make sure I write it all down. Now I've got the second term, and I start him at the 0th, and be sure as you work through that your exponents are adding up to 8. Whew, a lot of writing. Okay, now let's go ahead and get started trying to simplify this. On my very first term, this is going to 1. This is at 1 already, and the square root of a raised to the 8th is going to be a to the 4th. Okay? Now, for the second guy, we've got 8. I'm only raising that to the 7th power, so you might realize that's going to be a cubed times the square root of a. all right? Because I'd have 6 of them that could come out, which is 3 pairs. And then I have 2 times the square root of b. All right? Then I have 28 times square root of a to the 6th is going to be a cubed. And then I'm going to have times 4b. Hopefully you're okay with where I got the 4b. And then I have plus 56 times a squared square root of a times 8b square root of b. Oh, if those drive you crazy, it's not a bad idea to go back to the basic meaning. What does it mean to take something to the 3rd power? It means write out 3 of them and multiply. Rearrange it, clean it up, and that's what you should see. And then I have plus 70 times a squared times 16b squared. Oh, 56 a times the square root of a times 32 b squared square root of b plus 28a times 2 to the 6th is 64 b cubed plus 8 square root of a times 128 b cubed square root of b plus, let's see here, 2 to the 8th would be 256 b to the 4th. Whew, this is tough. But it's way better than writing out 8 of those and multiplying it all together. Now, last deal, I've got a to the 4th plus 16a cubed square root of ab. Are you okay that I multiplied everything that's outside the radical and what's inside the radical? And then I've got, I think, 112 a cubed b. Okay. And then I've got, what is that, about 448 a squared b times the square root of ab plus 1120, I believe, a squared b squared plus, I'm going to call Uncle on this. I could run it, but because of time, I don't want to. ab squared, square root of ab, plus, and by the way, whatever that is, that's the same number, 28 times 64, ab cubed, plus 8 times 128, b cubed, square root of ab, plus 256, b to the 4th. And just because of time, I'm going to let you do that last little bit of multiplication. Wow, what a mess. But there we be. Okay? Now, there's still one more thing that I want to take a look at, and that is to find a specific term. And I think what I'm going to do is skip number 1 here and go to number 2. How do I find one particular term? Now, I had a few people this last semester that would actually try to write out the whole mess just to find that one term. No, that is not your best bet. Use your binomial theorem, meaning this. This x squared plus y cubed raised to the 10th. My binomial theorem says that's the summation, as k goes from 0 to 10, of 10 things k at a time. First term raised to the 10 minus k. Second term raised to the k. All right? Now, if I'm looking for the one term that would have a y to the 12th in it, you have to ponder for just a minute, well, how do I get a y to the 12th? And you start looking here, because that's where your y is. Now, if he's already at the 3rd power, what do you want k to be to get to the 12th? Do you realize you want k to be 4? So that means that the particular term that I'm looking for is where k is 4. Well, once you have that decided, it is all home free from there. because you're going to have 10 choose 4, and you're going to have 10 minus 4, you're going to have 6. It becomes a very easy problem if you are willing to use your binomial theorem in order to get it. Now for 10 choose 4, sorry, I could run that in a moment in my head, but let's come out here. Here's 10 choose 0, 1, 2, 3, 4. It's 210. Okay, so it's 210 x squared y squared. And that's way easier than writing the whole thing out. The last one I want to look at is to find the fifth term in this expansion. So we have x minus 3y raised to the 8th, and I want the fifth term. Now, it does not hurt for you to go ahead and write out the binomial theorem on this. It would be, as k goes from 0 up to 8, 8 things k at a time, x to the 8 minus k, and you better be careful, grab that guy as a negative, negative 3y raised to the k. Whew. Now, if I can find out what k is, I am home free. Well, to get to the fifth term, you just have to think. The first term k is 0. The second term k is 1, 2, 3. Oh, k is 4. So I have 8 things, 4 at a time, x to the 4th, negative 3y raised to the 4th. In all honesty, I would grab my calculator there for the 8 choose 4, or I'd take a moment and run it. Or I say 0, 1, 2, 3, 4, it's 70. So I get 70 x to the 4th times 81 y to the 4th. Do you know where I got the 81? Then the only thing, that was the negative 3 raised to the 4th. The only thing left to do is do this multiplication. 5,670 x to the 4th, y to the 4th. That would be just the fifth term in that expansion. Okay? And then, oops, in recap, use your binomial theorem to expand out binomial to any positive integer exponent power. And you can also use that binomial theorem to get to any particular value. In fact, that's when I really rely on this guy, is when I'm looking for a particular value. Now, to get these values, which are called your binomial coefficients, to get your binomial coefficients, either use Pascal's triangle, which is very easy to make on your own, or use the NCR button on your calculator. And this is where you really need to be practicing this so that you will be competent with whichever process you choose to use. Okay, have fun doing this, and I hope you have enjoyed our lessons. I will see you.